So this lesson is the chain rule, and we talked about the chain rule briefly in the last lecture, but this is going to be a much deeper look at the chain rule and the power of it. First, I would like to look at the definition of chain rule. And it says, suppose that g of x is a differentiable function of x. Then if y is equal to that function raised to the power of n, then the derivative is going to be what looks a lot like the power rule because it is a power rule, except it has one thing added to it. The derivative is going to be n times the function raised to the power of n minus 1, but we have an extra step with the chain rule. And the extra step requires that once we do the power rule, we multiply by the derivative of the function itself. So let's look at an example. Example number 1. Example number 1, we have a function raised to a power. Now, if this had simply been x to the power of 6, then the derivative would be 6x to the power of 5, right? Because we know that if y is equal to x to the power of n, then we know that the derivative, according to the power rule, is simply going to be n times x to the power of n minus 1. And that's great as long as you have x to the power of n. And although x is a function, we typically separate it and view it in a different light when we talk about the chain rule. To repeat that, if you have x to the power of n, then the derivative is simply n times x to the power of n minus 1, which is exactly what we see here. But what makes this problem different is that we do not have x to the power of n, we have a function raised to the power of n. And again, if we have a function raised to the power of n, then we have to do the power rule, which is n times the function to the power of n minus 1. But we have this extra step here. We must multiply all of that by the derivative of the function. So let's do that now. Our function is 1 plus x cubed, and our power here is 6. So that's going to be 6 times the function itself, raised to the power of 5, because 6 minus 1 is 5. But since this is a function raised to a power, then we are going to multiply by the derivative of the function. Well, if the function is 1 plus x cubed, the derivative of the function is simply going to be 3x squared. Because the derivative of 1, being a constant, is 0, and then the derivative of x cubed is 3x squared. So we have to tack on this derivative of the function here. And next, I'm simply going to simplify. I'm going to multiply 6 times 3x squared, which gives me 18x squared, and then I'm just going to bring down the rest of it. So just to recap that, if y is equal to x to the power of n, then the derivative is n times x to the n minus 1. That's just the old power rule. But if you happen to have a function, g of x or u in this case, then the derivative is going to be the chain rule, which is n times u to the power of n minus 1 times the derivative of u. I guess the biggest challenge for learning this is trying to figure out how far do you go in order to simplify. Notice that I chose to stop here, because if I tried to multiply 1 plus x cubed times itself 5 times, that would be a very daunting process. That would be a challenge for me. And I'm pretty sure it would be a challenge for most mathematicians. and students as well who are not mathematicians obviously can struggle with that. So here's my solution to you. Obviously, if the solution is a multiple choice option, then you simply look for the one that is closest to this. And in all likelihood, this would be an option for any multiple choice. If it's a free response, I would say definitely stop here, because obviously trying to simplify this out by clearing parentheses would be very difficult to do. So it may be possible as you work through these that you may have an answer that seems to be different than the options in MyMathLab, and that just may mean that you have to do a little more simplifying in order to figure out which problem it matches with. Okay, so let's take a look at problem number 2. Example 2. Now this problem here is, let's see, y is a function to the power of 3, and we're adding to that another function to the power of 2. And again, we're just trying to figure out what is the derivative of y. Let's go back and review what we talked about last week. If we had something like this, y is equal to x cubed plus x squared. And again, x is a function and its derivative is 1. But if we had something like this, then we would say, okay, that's just simply power rule, right? In other words, we would claim that the derivative, y prime or f prime of x, is simply 3x squared plus 2x. Which is great if the function has to be x. But here, our functions are not that simple. We actually have functions raised to a power, and these functions are not x. So what does that mean? It means chain rule. Let me see if I can't write that. Chain rule. I'm going to write that only because I want you to have that fixed in your mind, that when you have a function raised to a power, it's going to be chain rule. So let's take a look at it. Let's look at this first function here. In order to find the derivative of the function, I'm going to do the power rule, which means I'm going to bring the exponent down, I'm going to multiply it by the function, and I'm going to raise it to the power of 3, because 3 minus 1 is 2. But remember, since this is a function raised to a power, I now have to add the derivative of the function, and the derivative of negative x squared is going to be negative 2x, right? The derivative would be negative 2x. And that's why we have a negative 2x here. In other words, the derivative of u to the power of n is n times u to the power of n minus 1 times the derivative of u. That takes care of that part. Now we need to bring down the plus sign. And once we bring that down, we will find the derivative of this function. Let me change colors here for clarity. To do the second part, again, I have a function raised to the power of 2 in this case, so I do the power rule, which is going to be n times u to the power of n minus 1 times the derivative of the function. Well, the function here is 5 plus 4x. And the derivative 5 plus 4x is going to be 4. Because the derivative of a constant, 5 is 0, that zeroes out, and the derivative of 4x is 4 using the power rule, because x to the power of 0 is just 1. And remember, derivative is also slope, or it can be interpreted as slope, and this would simply be a line of slope 4, right? So that's another way to justify saying that the derivative is 4. And again, the rest of this is just cleaning it up to make it look somewhat more appealing. And I chose to multiply the 3 here by the negative 2x, which gave me negative 6x, and then I brought down the rest of it. And then over here, I just multiplied 4 times 2, which gave me this 8, and I just brought the rest of that one down as well. And I'm going to leave this here. I could simplify it further. I could say, well, this is negative 6x, and I could go ahead and multiply that by the 1 minus x squared squared. And I guess technically I could FOIL that out to clear out parentheses entirely. But again, it doesn't do any good at this point to continue. I could distribute this 8 across here, and that would give me 40 plus, what, 32x? But I chose to stop here, which probably would suit me fine on a multiple choice test. Maybe the multiple choice option would have this one, or maybe I would have to go ahead and FOIL this out to further simplify. But if this were a free response quiz, I would say that for most teachers, most professors, if you get that far, they will probably be okay with it. So let's go up here and take a look at example 3. Example 3 is not only chain rule because we have functions raised to powers, but we have a product, right? We're actually multiplying. There's no plus or a minus in between. So we're going to have to use the product rule and the chain rule. So let's do that. Remember, the product rule says that if you have the product of functions, in order to find the derivative, you multiply the first function times the derivative of the second function. Well, the derivative of the second function is going to be 10 times 7 minus x to the power of 9. But then, since it's a function to a power, I have to multiply that by the derivative of 7 minus x, which is negative 1. That takes care of the first part. But then, the second part of the product rule says I have to multiply the second function times the derivative of the first function, which gives me this here. Now, some of you may be scratching your heads at this point and saying, what on earth is this guy doing? Let's go back and look at what we would have said last week. If we had y is equal to, I hate to do this, but I'm going to say x to the power of 4 times x to the power of 10. Now, most of you are probably thinking, well, that's easy. First, I would just say x to the power of 14 and go from there. But I'm trying to make an illustration here about the product rule. Last week, we would have said, well, the derivative is going to be the first function, x to the power of 4, times the derivative of the second function. And the derivative of the second function would be 10x to the power of 9. And then we would say plus the second function times the derivative of the first. And the derivative of x to the power of 4 would be 4x cubed. And again, that's great if you're doing x raised to a power, but we have functions raised to a power that are not x. So again, we have to employ the chain rule. So here we took the first function times the derivative of the second, plus the second function times the derivative of the first. So where did this 3 come from? Well, the derivative of 3x minus 5 is 3. So we would have to employ the 3 there. And again, from here we have to decide, okay, how far do we want to simplify this down? Well, I chose to go ahead and multiply this negative 1 times the 10. That gave me negative 10, and I brought the rest of it down. And then over here, I multiplied the 4 times the 3, which gave me 12, and I just decided at this point to stop. Let's look at example 4. Remember, if you have, in this case, we have a fourth root. Remember, if you have a fourth root, you can actually write that as the function raised to the power of 1/4. For example, if you have the fourth root of x, and you wanted to take the derivative, well, you could write that as x to the power of 1/4, and then you could just simply use the power rule. And that's what we're going to do here. We're going to, again, we're going to use the power rule, but we're also going to have to use the chain rule because we have a function here, right, that's raised to the power of 1/4. So let's look at it. Once we rewrite this as a function raised to a power, then we just do the power rule. So that's going to give me n times u, where u is the function, to the power of n minus 1. Well, how in the world did I get a negative 3/4? Well, if you take 1/4 and you subtract 1, in order to subtract 1, I have to have a common denominator, so I'm going to call 1 4/4. And of course, 1 minus 4 is negative 3. So that is where the power of negative 3/4 comes from. And then we have to take the derivative of the function itself. And this function happens to be a quotient, which means I have to take the bottom times the derivative of the top. And luckily, the derivative of the top is just 1. So I take the bottom function times 1 minus the top function times the derivative of the bottom, which is just 1. And then the quotient rule says I have to divide by the denominator squared. So this problem here employed a lot of different things. We had to do chain rule and we had to do quotient rule at the same time. Luckily, I have x minus x, which leaves me with 0 x's. And then I have negative 2 minus a positive 3, which gives me a negative 5, and then negative 5 times positive 1/4. That gives me a negative 5/4. And then I just chose to write the rest of it as is. So for my purposes, I'm going to claim that this is a sufficient answer here. So let's go down and look at the next section here, higher order derivatives. So far, we've looked at taking the derivative, and we really haven't talked about going any further with it. We could also find a second derivative, which is a derivative of the derivative, and we could find the third derivative, and so forth. And in physics, those actually have meaningful interpretations, and we will talk about that momentarily. But just for now, suffice it to say that if a function represents the position of a particle, then if you take the derivative of the position function, you have the velocity at any time, x or generally t, whichever variable you choose to use. And if you take the derivative of the velocity, that produces the acceleration function. So let's take a look here. We have y is equal to 1 over x. And we want to take the derivative. Well, since this is a quotient, this is a fraction, I could use the quotient rule, which means you take the bottom times the derivative of the top. Let's take a look at that. If we take the bottom, which is x, the denominator, if we multiply that by the derivative of the top, or the numerator, which happens to be 1, the derivative of 1 is 0. So there's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And the derivative of x is 1. Then we have to divide that by the denominator squared. And of course, x times 0 is just 0, and that leaves me negative 1 over x squared. So that would actually be the first derivative. So how do we get the second derivative? You get the second derivative by taking the derivative of the first derivative. So let's do that together here. I figured out that the first derivative is negative 1 over x squared. Well, let's take the second derivative. I would have to take the bottom, or the denominator, x squared, and I would have to multiply that times the derivative of the numerator, and the derivative of -1 is 0, minus the numerator. So minus a -1 is actually a +1, so that would be 1 times the derivative of the denominator, and the derivative of x squared, using the power rule, is 2x. And of course, this is all over the denominator squared, and x squared squared is x to the power of 4. So this term here would zero out, and the final answer is 2x divided by x to the power of 4. And if you cancel an x here and take out one of the x's in the bottom, that ends up giving you 2 over x cubed. So this is actually the second derivative. And notice that x cannot be 0. And that's one thing you need to train yourself to start doing, is trying to figure out what are the domain values. Well, the domain values would be all real numbers, because x can be any number except 0, because you cannot have a 0 in the denominator. So again, this is the second derivative, and we are finished with that problem. Let's look at example number 2. Well, example number 2 is a little more complicated, because we have a function raised to a power, and that means chain rule. So let's do the chain rule here to find the first derivative. Well, that's going to be, let's see, we have y is equal to u to the power of n. Chain rule says that that would be n times u to the power of n minus 1, but we have to go back and take the derivative of u. Well, if u is equal to x squared plus 10x, then the derivative of u is 2x plus 10. And that's why we have 2x plus 10 here. And the rest of it is just trying to simplify this down to something a little more meaningful. I chose to distribute the 20 across here and here. That gave me 40x plus 200, multiplying that times x squared plus 10x all raised to the power of 19. So I would claim that this is a good stopping point for the first derivative. And so how do we find the second derivative? Well, this is going to be a product, because we're multiplying two functions together, so we would have to use the product rule. I would multiply the first function times the derivative of the second function, plus the second function times the derivative of the first. And again, that's chain rule. So you may be wondering again, where in the world did he get this 2x plus 10? Well, I got 2x plus 10 because that's the derivative of x squared plus 10x. And that is how I got the 40 here, because the derivative of the first function is 40. So let's look at example 3. I have decided to post these lectures online, and hopefully you will take a look at it in D2L, and you will click on this video here, right? This is a video on higher order derivatives. So that's just a continuation of the lecture, and you can hear it explained from someone else who may do a better job, maybe even a worse job than I do, but it is extra help for you. So if at this point you're still struggling with the concept of the chain rule or higher order derivatives, I would encourage you to pause here, click on this link, and watch that video. Example 3. Suppose an object's position at time t is given by this position function, s of t is equal to 10t squared miles. So what does that mean? Let's talk about that for a second. Suppose you want to know how far an object has traveled if it is traveling according to this function. Well, if you want to know how far it's traveled after, let's say, 2 seconds, they really don't give us the unit of time here. So let's assume it's seconds. It could be minutes or hours. let's just say 2 units. So if I plug in 2, well, 2 squared is 4, and 4 times 10 is 40. So we know that the position at time 2 would be 40 miles. So what about the position at, let's say, after 5 units, 5 seconds or 5 minutes, 5 hours, whatever the case may be? If we want to know the position after 5 hours, then I would just plug in 5 for t, and of course 5 squared is 25, and then 25 times 10 is 250. So I know that after 5 minutes or 5 seconds, this thing has gone 250 miles. So I can track the distance this object has traveled. You tell me the amount of time that it has been traveling, and I can tell you its position. But they want to know, what is the average velocity between 2 seconds, let's say, and 5 seconds? Well, the average velocity is just the slope of the line at these points here, between 2 and 5. I'm going to try to draw a straight line here. So if I draw a line here between 2 and 5, if I were to find the slope of this line, then I would know the average velocity. And that's going to be the rise over the run. If you look at the change in y over the change in x, notice that if we drop from 250, let me change colors here. If I drop from, say, 250 down to 40, then my rise is going to be 210. And my run is going to be between 2 and 5. And of course, that's going to be 3. That's going to be the rise over the run. And 210 divided by 3 gives me 70. We could have used the slope formula, right? The change in y over the change in x. In other words, 250 minus 40 on top for the numerator, divided by the difference in x, the change in x. 5 minus 2 is 3. It's just the old slope formula from algebra. That's how you find the average velocity between 2 points in time. But the second part of the problem says, what is its instant velocity and acceleration when the time is 4 units? So let's say maybe 4 seconds, 4 hours, whatever the case may be. Well, as we said before, if you know the position equation, which we do, we can figure out the velocity equation by simply taking the derivative. And the derivative of 10t squared is going to be 20t. That's just the power rule, right? We bring the 2 down, multiply by 10, that gives me 20, t to the power of 1. So the velocity at any given time is 20 times t. To find the acceleration equation, we just take the velocity derivative, or the second derivative of s. And of course, the derivative of 20t is just 20. So what does that mean? That means that the acceleration is actually a constant, 20. To be specific, that's going to be 20 miles per unit squared. The velocity is 20 times t, and since they want to know the velocity at 4, then I just say, well, okay, 20 times 4 gives me 80, so the velocity at time 4 is 80 miles per unit. So let's say this happens to be miles per hour, then this would be, the velocity at time 4 would be 80 miles per hour. The acceleration would be 20 miles per hour squared. As I said before, I'm going to post this online, and hopefully you will actually stop and you will watch this video here. This is going to give you more explanation on the power of the first and second derivative to help you find the velocity and acceleration of objects at different times. And then I found this second video here, and it is rather lengthy, but it does provide a great overview of the various topics pertaining to the derivative that we have discussed so far this semester. So I would really encourage you to maybe put on a pot of coffee and actually watch this entire video, and I think it will help maybe clarify some of your questions. So this is higher order derivatives and chain rule, and I will see you next week. Thank you.